Hello, everyone. We've already talked about what correlation and regressions are, but in this video, we want to dive a little bit deeper into the implementation and interpretation of regressions. The example that we'll use for much of this video is to use a data set that was reported recently in an article in the Washington Post, where some surveys revealed that the percentage of mask wearing was negatively associated with the percentage of respondents from this survey who knew someone with COVID symptoms. And we worked through this example when we were talking about correlation. But what if we wanted to use these same data to predict how a change in public policy related to mask wearing might affect the rate of COVID? So in this case, we might test a null hypothesis that the slope of the relationship between mask wearing and COVID symptoms is 0. Now, if you recall, this null hypothesis refers to our true population and not our sample. And so as a result, we're using the Greek letter beta to represent the slope of this relationship in the true population. In this case, our alternate hypothesis is that the slope of the relationship between mask wearing and COVID symptoms is not equal to 0. So here are the data, or at least part of the data that I showed you before in the video on correlation, where for each state, we have the percentage of respondents that reported wearing a mask in public, and the percentage of respondents from this Facebook survey who reported knowing someone with COVID symptoms. And we can use these observations across 50 states to calculate deviations of each observation from the sample mean, and to calculate then the covariance between these two variables as the product of these two deviations from the sample means averaged across all of the 50 states that we're talking about. And we can see that in this case, the covariance between mask wearing and COVID symptoms was calculated to be negative 53.4. We can use this covariance then in the context of regression to be able to calculate the regression slope from our sample that's denoted by B. And the slope of the regression through these data then could be calculated as the covariance between mask wearing and COVID symptoms divided by the sample variance of mask wearing. And so we can use R to perform these calculations and save this calculated slope as an object called B, which is equal to the covariance between these two variables divided by the variance in mask wearing. And in this case, B is calculated to be negative 1.06. Now, since any regression passes through the mean value of the X variable and the mean value of the Y variable, we can then use this information and this slope to calculate what our intercept will be, the value along the Y-axis when X is equal to 0. So we can again calculate this in R and save the value as A, where it's simply the mean of the COVID symptoms minus B times the mean percentage of mask wearers. And in this case, the intercept is equal to 113.05. Now we calculated both the slope and the intercept separately, but we can also ask R to do this for us by fitting what's called a linear model. And we use the LM function to fit a linear model in R, where we report our response variable predicted by our predictor variable, specifying that the data frame that we want these variables to come from is called COVID in my case. So this is our definition of the linear model, and we're saving the results of this linear model in an object that I've called COVID_regression. And when we extract the coefficients from this model, we can see that R has calculated the exact same intercept and slope as we did before, but in this case, it's done it all at the same time using this linear model function. So we can use this intercept and slope to plot our line of best fit. And this calculated intercept and slope then represents our line of best fit, which simply means that it is the line that minimizes the residuals, meaning the deviations between each of these points and the line. And so in this case, we have an intercept of 113 and a slope of negative 1.06. Now, if you think quite carefully about what the intercept and slope mean, this is a good reminder that we need to be really careful about extrapolating our observations outside of the range of data that we've collected. I want you to think about this intercept for a minute. The intercept is our value of y when x is equal to 0. And what this relationship then is telling us is that if the percentage of respondents who regularly wear a mask were to be 0, that the model is trying to tell us that the percentage of respondents who know someone with COVID symptoms is predicted to be 113%, which is an impossible number. And so it tells us that something must happen to this line outside of the range of the data that would cause it to bend perhaps and no longer be on this linear trajectory. But at least within the range of data that we've analyzed here, the relationship appears to be linear. In addition to extracting the slope and intercept from our linear model, we can also extract what's called an R-squared value, which is simply the percentage of variation in our Y variable that is explained by variation in our X variable. And so we can use the summary command and the R-squared part of the summary command to extract that 73% of the variation in COVID symptoms among states can be explained by variation in mask wearing. In addition to calculating an R-squared value, we can also assess the significance of our slope using a t-distribution. In this case, our t-test statistic is calculated as the difference between our sample slope and the slope that we hypothesized in our null hypothesis, in this case, where beta sub 0 is equal to 0. So the difference between our sample slope and 0 divided by the standard error of our slope. And we test this t-distribution using a degrees of freedom equal to the sample size minus 2. We can report all of this information together by summarizing the linear model that we performed previously. This summary command then allows R to report to us all of the different aspects of our linear model. First of all, we get our estimate of the intercept and the slope that we extracted previously using the coefficient command. And for each of these estimates of the intercept and the slope, we have estimates of the standard error of that intercept and the standard error of that slope. We've got a t-test statistic associated with this standard error and this slope, and a p-value corresponding to this t-test statistic and our 48 degrees of freedom, which is equal to our 50 states minus 2. So if you recall then, our t-test statistic is based on the difference between our estimate and 0 divided by the standard error to calculate our t-test statistic. And we can then calculate a p-value from this t-test statistic based on 48 degrees of freedom. You can also see from this summary command that we have our R-squared reported here as 73% of the variation in COVID symptoms can be explained by variation in mask wearing. So now that we've run this regression, what can we do with this regression equation? Well, the first thing we might want to do is to predict some value of y based on some observed value in our predictor variable using this equation. So let's say we didn't have information on some other location or state or perhaps a province in Canada, and we wanted to use this regression equation to predict what the rate of COVID symptoms might be in that particular location. So let's say in that area, 85% of respondents reported wearing a mask in public regularly. What would we predict the rate of COVID symptoms to be based on our equation? Well, in this case, we can simply insert the value of 85, corresponding to 85% of respondents wearing masks, into our regression equation and calculate that the fitted value of y in this case, or the predicted value of y, would be equal to 22.6% of respondents knowing someone with COVID symptoms. We can visualize this from the line. Here we have 85%, and the line predicts a value of about 23%. In addition to calculating predicted values, we can also calculate the residuals, and that is the difference between each observation and the fitted value. So in this case, we might be interested in calculating the difference between the observed rate of COVID symptoms and what we would predict based on our mask wearing equation for a state like Wisconsin. And Wisconsin is shown by the blue dot here, where the residual is simply the deviation between the observed value and the predicted value on the line, or in other words, the length of this dotted line going up and down. So we can calculate the residual for Wisconsin then as being equal to the observed value for Wisconsin minus the fitted value for Wisconsin, which would fall somewhere right here along our regression line. So we can calculate what the fitted value ought to be based on our regression equation and find that this is 23.7%. And so based on our regression equation, we would expect Wisconsin to report COVID symptoms in 23.7% of respondents. But what the survey actually found is that 35% of respondents reported knowing someone with COVID symptoms. And so this represents a residual that is, first of all, positive. The Y value is above the line. And second of all, the magnitude of that residual is 11.3. In this case, measured in units of percent of respondents. Now, just like in our other statistical tests, we have certain assumptions associated with regression. First of all, that our observations are random and independent, that our Y values are normally distributed, and that the variance of our Y values is the same across all values of X. That is, that the variance in Y values is constant. And finally, we assume that the relationship between X and Y is a linear relationship. So how can we test some of these assumptions? Now, one of the most useful ways to assess the assumptions of regression is to perform what's called a residual plot, where we simply plot the relationship between our residuals and the values of the explanatory variable. So if you recall then, the residuals are just the deviations between the observed values and the fitted values that fall right along the line. And so we can use some R code to extract the residuals of our fitted model, and I've simply saved them in the original data frame here in my COVID data file. And I can then plot these residuals and add a horizontal line to them using this code here. And this is the plot that we then get from this relationship, and this is what's called a residual plot, where on the y-axis are our residuals, and that is the difference between the observed value and the fitted value. So these values up here that are positive residuals were values that were greater than the regression line. These negative residuals represented observations that were lower than expected based on the regression line. And these values along the x-axis correspond to the percentage of respondents who are wearing masks in each of those 50 states for which we calculated a residual. Okay, and this plot tells us an awful lot about many of the assumptions of our regression model. First of all, what we're looking for in this residual plot is for a roughly symmetrical cloud of data points in and around 0. This lets us know whether or not there are any extreme outlying observations or whether there are patterns in the residuals suggesting a nonlinear relationship, or perhaps some indication that the variance in the residuals increases with increasing X or decreases with increasing X, which would be represented by a fanning out or a fanning in of the residuals, where there's perhaps less variation in residuals down here, and imagine a scenario where there was a lot more variation in residuals down here, or perhaps the opposite, where we get a bit of a wedge shape in these residuals, where there's less variation at low values of the X variable and much more variation in residuals at high values of the X variable. So these residuals actually look quite good. We've got a nice cloud of data points centered around 0. There doesn't seem to be any particular pattern in the residuals. They look like they're just a cluster around that value of 0. And there doesn't seem to be any fanning out of the residuals or fanning in of the residuals. So this residual plot actually looks pretty good. But here are some residual plots that don't look very good. In this plot, you can see that there is one very large outlying observation that has a very high residual, which would be cause for concern. In this plot, there are clear patterns in the residuals, where low values of X tend to be associated with positive residuals, intermediate values of X tend to be associated with negative residuals, and very high values of X tend to be associated with positive residuals again. And this is indicative of a nonlinear relationship between X and Y. We can also get patterns in the residuals that are indicative of a non-normal distribution of the residuals. And here we can see that there's not a clear cloud around 0. In fact, there are very few observations that fall in and around the regression line, and most observations fall either well above the line or well below the line, which is going to lead to a bimodal distribution of residuals. And finally, we might find that our variance in residuals is not consistent across values of X. And so what I mean by variance in residuals is simply how much these residuals differ above and below 0. So here we have very little variation, and that variation gets bigger and bigger and bigger as we're getting increased values of X. And that's what I mean by this fanning out of the residuals. They look like a triangle or a wedge shape. And so when the variance in the residuals is not consistent across all values of X, this is what's referred to as heteroskedasticity, that the variance in residuals changes across values of X, and this is a violation of one of our assumptions of our regression models. In addition to the residual plot, we can also assess the normality of the residuals using histograms and QQ plots like we did before, where in this case, we're looking for a typical bell-like shape in the residuals and not a high skewness or bimodality in those residuals, as visualized either in the histogram or in the QQ plot. So when we perform a regression, our goal is to estimate both the slope and an intercept. And this is really different from a correlation, where there isn't really any logical reason to treat one variable as the X and one variable as the Y. In the case of a regression, we do have a clear predictor and a clear response. In order to assess the significance of our regression, our data must be random and independent, with Y values that are normally distributed, and with variance in our Y values that is consistent across all values of X. And finally, in order to perform a linear regression, we need to actually have a linear relationship between our X variable and our Y variable. We can assess these assumptions by plotting our data and looking at the residuals to detect whether or not there are any outlying observations, any indication of nonlinearity, or any changes in the variance of our residuals across values of our X variable. And finally, we always need to be careful when creating predicted values to not extrapolate and predict beyond the range of our observed observations for which the regression was generated.